Today I will discuss about the analysis of XRD data. So, I have shown you the instrument and that instrument is used to take the data from a sample. So, this if you give sample to operator, generally they will do experiment for safety reason and they give you a set of data like this. So, here sample is sodium chloride salt, whatever we eat salt. So, that salt in powder form. Now, X-ray is used for this experiment is copper K alpha, its wavelength is 1.54 angstrom. So, basically copper target and nickel filter is used to get this copper K alpha on the sample. So, this method is powder diffractometer. So, powder diffractometer. So, geometry is like this. So, this is the X-ray source. So, X-ray is coming and falling on powder sample. Now, this is the direction of incident X-ray. Now, the diffracted X-ray in different directions. So, that direction is 2 theta with respect to this incident direction. So, a detector it just move in a circle to record the diffraction data. So, if you plot this data, so this data you will see in a plot like this. So, there are some peaks of different intensity and also different peak width. So, from this data, so what you are seeing? You are seeing there is a number of peaks is called Bragg peaks and the different peaks have different intensity and also they are not very sharp peaks, but there is a width. Okay. So, this peak position in terms of angle 2 theta. So, here you will be able to see angle 2 theta. So, that is the detector angle with respect to the incident direction of X-ray. So, generally we plot intensity versus 2 theta. So, the position of the peaks in terms of angle, intensity of the peaks and width of the peaks, all these three contain information about the sample. So, we have to analyze the peak position in terms of angle, then peak intensity as well as peak width. So, these three will give us information about the sample. So, what are the information we can get? So, first very important information we would like to know, that is crystal structure, the whatever sample we have taken, what is the structure, crystal structure of that sample that we would like to know. So, this crystal structure in one hand and in other hand we have diffraction pattern. So, relation between these two is unit cell corresponds to line or peak position. This is basically Bragg angle and the atomic position in unit cell, that corresponds to line intensity or peak intensity. So, here mainly I will discuss this peak position and peak width, but I will not discuss this intensity part, because this slightly complicated, and for higher study we would like to discuss this part, but this other part is not very difficult one. So, at this stage I would like to discuss only this line position or peak position, and from there, as well as peak width, from there what are the information about the sample we can get. So, here this actually we would like to we will be able to know about the crystal structure in terms of unit cell. What is the size of the unit cell, what is the lattice parameters. So, that we will be able to find out. So, that diffraction pattern I have shown you. So, there are many peaks. So, first task is to index those peaks. So, that is called indexing patterns of XRD. So, crystal structure, there are 7 crystal system and 14 Brevis lattice. So, out of 7, one system is cubic system, cubic crystal. So, that is the simplest one. So, I would like to take this example, since the sodium chloride that data I have shown you, that is that sodium chloride have cubic structure. So, I will discuss in terms of cubic structure, but for other structure also similarly one can do the analyze the data. So, in case of cubic crystal, so you know the relation between the lattice parameters and the planar spacing d. So, d equal to a by square root of h square plus k square plus l square. So, h, k, l are Miller indices. So, from here and this is from crystal part, from crystal we know this relation. Now, this for XRD patterns. So, that pattern we find we get. So, that follows basically this 2d sin theta equal to lambda, n equal to 1 we have taken for only first order we are considering. So, if I put this d value here and square on both sides. So, you will get 4a square sin square theta divided by h square plus k square plus l square equal to lambda square. Okay. So, I can rearrange and I can write sin square theta by s equal to lambda square by 4 a square. Now, you can see from this relation, for an experiment we use a particular lambda. So, lambda is constant and we use a particular sample. So, that sample that lattice constant a is also constant. So, this part lambda square by 4 a square is constant, and that is equal to sin square theta by s. So, now theta is the Bragg angle of different peak and s is basically sum of the square of the Miller indices. So, from pattern XRD pattern there are many peaks. We can tell this peak number 1, peak number 2, peak number 3 here, peak number 1, peak number 2, peak number 3, 4, 5. So, this is a peak number and these peaks have this angle. So, this 2 theta, from there we can find out theta. So, we can easily calculate sin square theta. Now, sin square theta divide by s is this, s is this one. Okay. So, for different s there will be different HKL. So, what are the possible s? S can be is always integer, s is always integers. You can because HKL is integer. Okay. So, s will be integer, means h square plus k square plus l square is always integer and lambda square by 4 a square is constant for all peaks. So, for all peaks this will be constant. So, sin square theta by s, sin square theta experimentally we are getting from the peak position. So, this so this s, so sin square theta will calculate for different peak, okay. And this you can write s equal to h square plus k square plus l square. So, it can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, just you write up to say 20. Here I have written up to 8. So, now for 1, so only one combination 1 0 0, this HKL, this value is only possible. So, this is basically it is a 1 0 0 family. So, it is not only 1 0 0 plane, it is the 0 1 0 0 0 1. So, all sorts of planes basically under this. So, this it is not one plane, but it is a family of planes that we tell, we write in second bracket. So, 1 0 0. For 2 only HKL value can be 1 1 0. Again it is not one plane, it is the plane of family of some planes like 1 1 0, 1 0 1, then 0 1 1. Okay. So, for 3 1 1 1, for 4 2 0 0. So, no other combination is possible. 5 2 1 0, 6 2 1 1, 7 there is no possibility to have any combination of HKL. So, 8 2 2 0. So, 9. So, you can go 3 0 0. So, one can add not only 3 0 0. So, other combination may be possible. So, that one has to see. So, now you S is in your hand. Now, sin square theta also you have got from the peak position. So, the sin square theta by S by 1, by 2, by 3, by 4, just if you make a table, then you will see that it again as I mentioned that this has to be constant, this has to be constant. So, you will get a value, So, that value for all peaks that will remain constant, that will be same value. So, now from that value basically one can find out the A value, lattice parameter, that is A value one can find out in case of simple cubic. So, in cubic there are basically 4 category. One is simple cubic, another is face centered cubic, then body centered cubic, another diamond also this in the cubic system. So, it is not the Brebis lattice, diamond is not the Brebis lattice. So, Brebis lattice is these 3, but diamond it is basically FCC structure with additional lattice point, additional more 4 lattice point in the face centered cubic. So, basically you know that in simple cubic the number of lattice point per unit cell it is the 1, face centered cubic it is the 4, body centered cubic it is the 2, and diamond in case of diamond it is 8. Okay. So, so this here I have written that for in case of simple cubic, so this generally this all sorts of planes are this not all sorts of plane. So, diffraction can be obtained from all planes, but when it is FCC face centered cubic. So, diffraction from all planes does not arise. So, only this 1 1 1, 2 0 0, then 2 2 0, then other peaks arise. So, in case of body centered cubics 1 1 0, 2 0 0, 2 1 1, 2 2 0. So, how you will find out? Basically, you will find out when sin square theta from the pattern you will get and divide by this 1 2 3 4 5. So, then you will find that only for these peaks, okay, you are getting constant value, you are getting same value. For other s you are getting different value. So, that means that peaks are not there. So, these peaks are absent. So, so that way you will be able to identify that in case of simple cubic all sorts of planes are there for face centered cubic and body centered cubic and diamond. Okay. So, these peaks will be available. So, from that itself you can identify that in cubic whether it is face centered, whether it is body centered, or it is diamond structure or simple cubic. Okay. So, what we saw that this basically the proper set of integers for S is not hard to find. The following characteristic sequence of diffraction peaks can be described by their sequential S value. Okay. So, whatever in table I showed. So, this in case of simple cubic basically S value. So, here it is said, so whatever that pattern you have seen. So, this peak number 1, 2, 3, 4, 5, okay, if you just give number, and then those peaks will satisfy the with this S value. Okay. If it is simple cubic, so first peak, so S equal to 1, second peak 2, S equal to 2, third peak S equal to 3. So, that way for all sorts of S value it will satisfy, only missing is 7 and then 15, because this for these numbers you cannot get any you cannot get any set of HKL value to for that S value. Okay. S value is A square plus K square plus L square. Now, in case of body centered, so first peak, so for that S equal to 2, for second peak S equal to 4, for third peak. So, all even number. So, body centered cubic, in that case S value is even number. Okay. Now, face centered cubic, that S value for first peak it would be 3 and then 4, 8, 11 like this. In case of diamond, so S value will be for first peak 3, 8, 11, 16. So, this sequence is written from you see this there are details reason for that, it is basically scattering, atomic scattering from crystal. Okay. So, this basically intensity of the Bragg peak, it depends on the structure factor, and in structure factor basically atomic positions are included. So, so from all planes these diffractions are not allowed. Okay. So, for only these S value the one can get diffraction for this simple cubic or body centered or face centered or diamond cubic. Okay. So, this when you will get data from the lab, so they are giving you the raw data. You have to plot intensity versus 2 theta, then you will see these different peaks at different angle. So, first task is to identify the angle or calculate the angle, Bragg angle, and from there you calculate sin square theta, and then you divide the sin square theta by 1, 2, 3, 4, 5, 6, not 7, 8, 9, 10. Okay. So, then you find out this which values are this constant sin square theta by S, which values are same. So, so those S value are basically for those peaks whatever you are seeing, and if you see that S value is 1, 2, 3 all sorts of value. So, then it is simple cubic. If it is only even value 2, 4, 6, then it is body centered. If it is 3, 4, 8, 11, 12, so then it is face centered, and if it is 3, 8, 1, 11, 16, then it is diamond cubic. Okay. So, so this is the analysis of the pattern, XRD pattern you have observed. Now, this whatever the sin square theta by S. So, whatever the same for all peaks. So, that value you know, now lambda value you know. So, you can calculate A value, okay, for simple cubic. So, so this whatever this data I showed you initially, this here. So, this there is no indexing of these peaks, is the sodium chloride sample. Now, whatever the way I told you from following that procedure, you can just identify indexing the peaks, Okay. So, these the peaks of sodium chloride, Bragg peaks from sodium chloride. Okay. Here you can see this just for curiosity, you can see that what are the this sodium chloride is the FCC face centered cubic. So, here whatever for face centered cubic, whatever I showed you that I think yes, I showed you this for face centered cubic. So, peaks are 1 1 1, 2 0 0, 2 2 2, Okay, these are the peaks only you will see, and this after that other peaks. So, exactly here you can see 1 1 1 2 0 0, then 2 2 0, this is the third peak, then fourth peak will be 3 1 1. So, 3 1 1 means 9 11 12. So, this for 12 S equal to 12 after, yes, for face centered, what I told you that S equal to 3, S equal to 3 means 1 1 1. Then I showed you this S equal to 4 means 2 0 0 second peak, then third peak for face centered cubic 8. Okay. So, that is 2 2 0. Okay. Then next value is 11. Okay. So, next fourth peak is 3 1 1 9 plus 1 10 plus 1 1 square, of course, this 11. Then this one is 12 1 2 2 2. So, next S is 2 value. Next peak is 16, next peak is 16 4 0 0. Okay. So, when from sin square theta by S you are getting all these value constant, all these value same. So, then from there, from that S itself you can tell what is the plane, it is the 1 1 plane. So, this peak is from 1 1 plane, this peak is from 2 0 0 plane. Okay. So, this way one can identify the peak, and also one can tell what is the structure. So, I discuss just taking example of simple crystal. So, because this is the easiest one, but for other one also you can do. For that you have to for simple cubic, that relation was D equal to A by square root of H square plus K square plus L square. So, for other structure you have to know all this information. Here I have listed, in any solid state physics book you will get. So, I followed whatever I am showing here. So, all these things I have noted down from the book, that introduction. I think I will write the name of the book, that is Introduction to X-ray Diffraction. Introduction to X-ray Diffraction. I will write Introduction to X-ray diffraction, X-ray diffraction by B.D. Coolity. Okay. This is very famous book for X-ray diffraction, basically the experimental aspect of X-ray diffraction. So, it is a nice book. So, from that book only I have noted down all this information. So, for cubic structures, 1 by d square equal to a square plus k square plus s square by a square. For tetragonal, what is the relation? For orthorhombic, what is the relation? Okay. What is the angle between these two plane H1 K1 L1, H2 K2 L2? Okay. So, in case of simple cubic, in case of cubic structure, so we do not need alpha beta gamma, because that we know this 90 degree. Okay. But in case of other structure, say triclinic or monoclinic, so angles are different. So, so here all relation you can see, this is basically ABC and HKL value. Okay. So, from XRD pattern, you are indexing When you are indexing, that means you know the HKL value of this of the planes corresponds to that Bragg peak. Okay. HKL value is known to you for different peaks, and then lambda is known to you, and then you can find out d value also you can find out from this sin square theta value. Okay. Sin square theta, lambda, then from there basically you are indexing HKL, and then from so this for that you are taking help of S equal to H square plus K square plus L square. Okay. So, so in case of simple cubic, it is a simple, not simple cubic. In case of cubic, it is that calculation is simple, but for other system, so it is same way one has to proceed. It's so you need not only A, you need A, B, C. Okay. So from one peak you cannot, from one relation you cannot find out this value. So you need more relation. So you need to analyze more number of peaks. Okay. So so from this relation, whatever I showed you here, from this relation and the procedure I told you how to indexing the Bragg peak. So using this knowledge one can basically find out the determine the structure of the crystal. Okay. So then I told you that I will not discuss about the intensity of the peak, but I will discuss about the, so far I discussed the position of the peak. From there this you can find out the unit cell of the crystal and what are the lattice parameters. Now this width of the peak also very informative. So from the width of the peak one can find out the crystallite size of powder particle. Whatever the sample we have used this powder form. So there are millions and millions particles are there. So what is the size of those particles? Crystallite size, not physical size. So one can find out. So there is a formula, ready-made formula to find out the crystallite size. So this is called Scharer formula, Debye-Scharer. So Scharer formula, that is T, the size of the crystallite size T equal to K lambda by B cos theta. So T is the crystallite size, again crystallite size and the physical size of the particle are not same. Generally crystallite size is less than the particle size. So here basically from XRD, X-ray diffraction we can find out crystallite size. So that may be equal to the size of the particle, or it may be less than that, it cannot be greater than that. Okay. Lambda is the wavelength, theta is the Bragg angle of peak. So you take just one peak of higher intensity. So for that peak what is the theta, that from the diffraction pattern, XRD pattern you can find out theta, and k is here, this not k is not Boltzmann constant, it is a k is a constant and its value depends on the shape of the particle. So generally this for spherical shape of particle, this k value is taken is 0.9. So sometimes k people take just k equal to 1, but it is not exact. So theoretically people suggest for different value, for spherical value this k is taken is 0.9. Okay. So, B is known, lambda is known to us, theta also we can get from the peak. Now, what is B? Okay. So, just you from your excited pattern you pick up a one peak, okay, and magnified you just plot in a magnified with magnification. Okay. So, now this B is basically B is full width at half maxima. So, full width at half maxima. So, what is that? So, this peak, what is the intensity of this peak? So, this I max, intensity maximum at this peak. Now, half of this maximum intensity at this position, what is the width? What is the width in radian? What is the width in radian is the angle. Okay. What is the width in radian? So, that is basically B. Okay. So, from Bragg peak itself you can find out this just B and theta peak position theta, not 2 theta, from here you will get 2 theta, from that you have to find out theta. So, you can use this relation. So, theta means cos theta you know, lambda you know, k is generally for spherical shape it is a 0.9 and then from the width of the peak you can this that is B and you can calculate the size of the particle. It is not size of the particle, size of the crystal of the crystal, okay, or crystallite size we tell generally. So, this way from peak position, from peak width we can get the crystal about the crystal structure, we can get the information about the particle size, and peak intensity we can get lot of information. So, there are this is a very vast subject, there are many more things, but I think that is a basic things I discuss here. So, that is enough for this stage. So, I think this if you should practice using different excited patterns even from the say internet, and try to find out just how to identify the peaks and their corresponding HKL value, and how to find out the lattice constant, how to find out the this particle size. Okay. So, I think I will stop here. Thank you for your attention.